problem is, so you ask Bob the programmer, write me a bunch of test validated code. Well, he ask you like, well, what am I validating? Like, well, this thing is gonna spit out code, and so your program has to be universal code prover. He's like, well, I can't do that.
Yeah.
It's like, what do you mean it's gonna spit out stuff? It's like, well, I'm gonna give it prompts to generate functions and programs, and then your program is supposed to then compile it and run it and make sure it produces the output. Right. So a human can do it, but it takes time. And so the advancement is that they've trained a model to be able to do that part.
Welcome to Practical AI, everybody. My name's Jeff. I'm here with Peter Lin. Practical AI is brought to you by Pocket AI. Pocket AI is a tool you can use to edit the weights of your model. With Pocket AI, you can prune over 60% of the weights in your model while increasing accuracy. Peter, the Chinese are at it again. They've come out with a paper that is interesting, maybe shocking. It has a little bit of uh-oh factor in it. So tell us what this paper is.
So it's a paper out of a research facility in China, but using the same basic idea as AlphaGo, right? AlphaGo was a system created by DeepMind to play Go. And after they beat Lee Sedol, they then trained AlphaZero, which only had the rules for Go, and then it played itself to learn. And after about, I think it was a couple of weeks, they actually surpassed AlphaZero. I mean, AlphaZero surpassed AlphaGo. And so this is the same idea of like, how do you create data to train? Because the problem that people have been saying for the last year now, year and a half, is we're out of data. Well, so then the obvious question is, can you use synthetic data? The problem with synthetic data is it ends up causing the model to collapse and get worse because you're not validating the output. So in the case of AlphaZero, because it knows the rules, it can validate what it produced, right? Because you can actually play the game and know, yeah, it won or it lost. And so that paper applied the same basic idea. We can generate new data to train, but that data has to be validated. And then when we can validate it, we can tell the model, no, you learned the wrong thing, or yes, you learned the correct thing.
Okay, so the Chinese in this particular case, this research group, they've basically figured out a way in at least one band to create synthetic data that is useful for more training.
Yeah.
And what you're saying is that historically, synthetic data is problematic. It can cause the model to collapse. And on the flip side, though, human data has limitations, right? So I think with the AlphaGo scenario, I think we've talked about this before, but if you only use like chess or Go, human moves, it's only learning a small band of stuff, because what if humans haven't figured out every possible move in chess or opening or whatever? And I think
Yeah.
this is kind of an example of that, right? Where all of a sudden you just give it the rules without the negative side of human data only,
Yeah.
and let it go, and it's expansive in terms of its ability to do things that we wouldn't have expected.
Right, because humans have a bias, right? Like we have taste, we have preference for certain things. Like if you ask someone to design a chair, most people would design a chair with four legs because that's like the most common kind of chair that you've seen. Or if you ask someone to design an office chair, they'll design one that looks like an office chair with a regular single seat post, legs and with wheels, and it's got a back and lumbar support, all that kind of stuff, right? So humans have a certain bias, whereas machine doesn't have that. It has no taste, so it can just generate random stuff and figure out what works.
Okay, but a big part of this is that validation part. I'm going to bring up that screen again, and let's just talk again about why this is important.
Yeah.
If you're maybe the chair is a good example. If you're going to have it come up with new chairs,
Yeah.
the system doesn't necessarily have a mechanism to validate that. But if you're having it write code, you could have
Right.
it run code and see if the code actually runs, right?
Right. Exactly.
So tell us a little bit about like how they're doing this with this sort of self-play loop and how they validate.
So basically, right, the key part is it's verifying, right? So that bottom part, solve, and it verifies the actual output. So the top here, so that little icon is the Python icon. Right, so it says, okay, give it a task, and it tries to generate code. And so the three things that they observe that it can do abduction, deduction, and induction, which is three different kinds of reasoning, but we won't get into that today because it's a longer conversation. So basically, they're able to kind of look at what it was doing, but more importantly, that the key factor is you can verify what it created, right? Because if you don't verify, i.e., actually run the code, make sure it compiles and runs and produces the output that you want, without that, the model would collapse, right? It's because you're verifying the output that you can then refine the model and keep making it better.
Okay, so this paper then, the advancement, the thing that's unique about it is that they basically were able to come up with this
Yeah,
verification process because
yeah,
people have obviously been trying to create synthetic data for a while, but in this
yeah,
instance, they figured out a process, a verification process, this self-play loop that
yeah.
actually works, and therefore the model goes off and just learns like crazy. Is that right?
Yes. Yep. Yep. Yeah, and this is not new, right? Like the the Pentagon started an initiative to try to replace C with Rust last year,
Yeah, it was a
right?
DARPA
So
project, wasn't it?
yeah, and so I mean these ideas have been floating around in academia for a long time. I mean, so it's not this is not a new thing,
Mhm.
right? It's been around for at least a decade or longer, but it just took this long for things to progress to this point where you could have a model that could then validate things.
Okay.
Because in the past, someone would have had to have written handwritten code to validate the output. But the problem is, so you ask Bob the programmer, write me a bunch of tests to validate the code. Well, he ask you like, well, what am I validating? Like, well, this thing is gonna spit out code, and so your program has to be universal code prover. He's like, well, I can't do that.
Yeah.
It's like, what do you mean it's going to spit out stuff? It's like, well, I'm going to give it prompts to generate functions and programs, and then your program is supposed to then compile it and run it and make sure it produces the output, right? So a human can do it, but it takes time. And so the advancement is that they've trained a model to be able to do that part, so they can automate it.
Okay, so let's take that C to Rust scenario. So this this model, this and plus this sort of method would
Yeah,
allow someone to do that because they could essentially have a model that converts C to Rust, and they could put it through the this method
hmm,
and the AI, and it would all of a sudden, instead of training on human C code
yeah,
examples, which is what happens today predominantly,
yeah,
it would just know the rules of C, writing C and
exactly.
Rust, and it would write its own code, and then it would go through this verification process, and
Yeah,
it would say, "Hey, that C code that you ran works. The Rust code that you just wrote or converted to works,
yeah.
and so therefore that yes, all of a sudden you're going to have an AI that'll just do it, and you won't have a bunch of human interference on it.
Right. In theory, right? So that's the theory of how you do it, but in practice, it's much harder than that because,
Of
so
course.
let's say you're a Pentagon, you're saying, okay, there's something like a billion lines of C code out in the world. A lot of it is 20, 30, 40 years old, and a lot of it has vulnerabilities and security bugs and a bunch of other stuff, right? And so the Pentagon, you care, you want the thing You want software and systems to be safe. Well, how do you systematically convert arbitrary human written code to another language and have it be valid? So if you follow computer science theory, you can look at the syntax structure of C, syntax structure of Rust, and you can map it to each other. So that part is straightforward. But when human write programs and code, humans don't always write the most pretty code. Most code is pretty ugly.
Yeah.
And so then the problem is, okay, well, how do you arbitrarily translate really terrible code? It could be someone that just learned 3 months ago, and so they're just writing garbage, but they don't know it's garbage,
Sure.
right? And so when you look at models like GPT and Anthropic, they've trained on the internet, which means they've consumed all the open source code out there. And by and large, I would say 90% of the code is garbage. I mean, it's just not really good code. It's got bugs, it's got design errors, it's got design issues, it's got limitations. It's probably got some like buffer overflow areas that could easily be exploited. Um, and so you need to train a model that then knows what good code is
Mhm. Could
in
you do
order to
that?
have.
Could you do that more easily with this verification setup than you could historically?
So I think what they've done is they've shown that you can create a model to validate, right? And so they made it for this very narrow case of Python, and probably just for specific use cases they have. It's probably not a formal proof engine in that it's mathematically rigid and mathematically valid because Python language does not have an official specification.
Yeah.
Like other languages like C sharp, C, C++, Java have a formal definition that's mathematically rigorous. And so you can actually prove a Java program is valid because it's well defined. Python is not. So historically that's been an issue with Python is they have a reference manual for Python, but there's no specification. And so there's versions written in C, C++, Java, C sharp, and the languages, and they're not compatible with each other.
Well, plus, I mean, humans like we just do stupid stuff and
Yeah.
rewrite bad code for a reason and whatever, right? So we could end up in a scenario where it's like if you have the perfect data model, it doesn't mean you implement that data model out of the book right into your organization. There's always edge cases and reasons why you make decisions to do something different. So you still need probably some human validation that
Yeah.
yeah, that was clean code or the 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 C to Rust model or code creator that had yeah, it validated that the code ran, but also that line of code was 10,000 times longer than it needed to be because it
Yeah.
was, a human would know that this is not an efficient line of code or whatever, right? You just got some,
Because someone's working late at 3 in the morning, and they wrote some code to patch something up to get to work.
yeah, yeah, yeah. Okay, so what's the uh-oh thing then with this?
Well, the other thing was that they noticed that as it learned to reason, it was doing things that were not desirable,
Okay.
right? So again, that goes back to the whole alignment issue. That oftentimes models fake alignment. In this case, they observed that it was learning reasoning that was kind of troublesome.
Oh, like Skynet type stuff.
Not well, I wouldn't say Skynet because I mean it's at the end of the day it's just still code,
Yeah.
but it's stuff that like you'd be like, no, that's if you deploy that code, you get fired,
Okay.
basically. So from a program perspective, yeah, that's a no because you're gonna get canned.
All right, last question then. So, self-training or this validation loop,
Yeah.
is this an important advancement in AI?
I think it's a good breakthrough to show that it can be done, but I think a lot of people already suspected that you could do it. It was just a matter of like actually doing it and then writing the paper, which is it took a lot of work.
Yeah, good. All right. Well, thanks, Peter. That's super helpful. We will be back next week with another episode. You can always follow us on Spotify. If you have questions, thoughts, or comments, we'd love to hear them. And until next time, we'll see you on the next Practical AI episode. Thank you.